Okay, so today we are doing something called the Fundamental Theorem of Calculus, Part 1. The word fundamental obviously implies that this is a huge deal. There's a big chunk of the AP test that comes from the fundamental theorem, and it kind of sets us up for what we're going to be doing with the rest of this class. So big deal here, no pressure. So one of the definite integrals formulas that we learned yesterday, I want you guys to write this down. So from 0 to b of x dx, this is one of the ones, not yesterday actually, I guess that's a lie, a couple of classes ago. We learned this formula and we have that it is 1/2 b squared. Now, as I was moving around, listening to some of you guys talking, I noticed that some of you were starting to piece things together. And you were probably right if you were starting to piece things together. We want to expand it a little bit though. So in this last class, we talked about how this has a lower bound of 0, and this formula only works so far for a lower bound of 0. We want to expand it to this, the integral from a to b of x. Okay, so remember what this represents. I don't want us to get too wrapped up in formulas and forget what this notation represents. It represents the area under this function from this point to this point. Okay, so let's get a little bit of a graph going. So let's set up, so x is just the line, y equals x, looks like that. And then if we want to go from point to point, this is what we're trying to find here. Okay, so we're trying to find this area right here. That's our end goal. Okay, so rather than doing this kind of generally, let's do a specific example. Okay, so let's do the specific example of 2 to 5. Okay, so call this 2, call this 5. So the way that we had been doing this yesterday is we had to kind of split it up so that you'd have a 0 there. However, this time we don't have a 0. So here's how we're going to do it. If we want to find this area right here, let's find the area of the whole triangle from 0 to 5 and then subtract away this smaller triangle. Okay, so we're going to go all the way from 0 to 5, which is more than we need. We're going to do this whole larger triangle right here. But then since we don't want this little part, we're just going to subtract away the area from 0 to 2. Okay, so now we can use this formula that we've got right here up above. So from 0 to 5, we plug into this formula. So 1/2 times 5 squared. And then minus now from 0 to 2. Again, just plug right into this formula. So 1/2, but this time times 2 squared. All right, so we simplify it up. Lots of fancy things happen. All right, so this is 1/2 of 25 and then minus 1/2 of 4. So we end up with 21/2. The 21/2 is not important. It is this step that's important. And like I said, some of us were starting to notice this yesterday. And of course, it's a very anticlimactic moment when on the next page I'm like, what do you notice? And then I just give you the answer on a video. Normally, if we were all together in class, I could ask you what you would notice and then hope that some of you guys had kind of seen the pattern. But on the next page, what you should be noticing is this part of the formula right here. 1/2 times something squared. 1/2 times something squared. Look at x. Think about some of the stuff that we were doing before the final. The antiderivative is what you should notice. You should hopefully notice that the antiderivative of x is 1/2 x squared, which is exactly what you see right here. Okay, so that's what I mean by this next part right here. This is what I'm hoping you would notice. All right, so what do you notice? 1/2 x squared is an antiderivative of x. Okay, now notice I don't say the antiderivative. We say an antiderivative because there are an infinite number of them. But like this is a huge deal. The stuff that we did first semester with derivatives, and then we kind of launched into antiderivatives a little bit right before break, and integrals, they're introduced and they're always treated as if they're two separate topics completely. Derivatives, integrals, separate. Derivatives do slope, integrals do area under the curve, no connection whatsoever, two pieces of calculus. And that's just, it's not true. It's so far from the truth. So it's not a coincidence. That's what I've got written here. It's not a coincidence that's an antiderivative. These two are so closely related, and we get this theorem that so wonderfully links them together. So the last thing I want you to notice here This is an antiderivative. 5 is the upper bound right here. 2 is the lower bound right here. So what you do, and this is the trick, and this is the theorem that we're going to write down, is you find an antiderivative, plug in the upper bound, plug in the lower bound, and subtract them. And it works every time, every function that you're able to take an antiderivative of, not just the ones that involve geometry. So as you can see, compared to what we did when we did some of those problems the long way, I'm sure you realize that the shortcut is absolutely glorious. Okay, so the fundamental theorem, here it is. So assume that f of x is continuous. We know that continuity is usually a huge part of a lot of these theorems. If f of x is an antiderivative of little f on a to b, here's what this says. The antiderivative from a to b of f of x is equal to the antiderivative with the upper bound plugged in minus the antiderivative with the lower bound plugged in. Okay, so this basically does the same thing that we did with the triangle. This one goes all the way from a to b. This one goes all the way from 0 to b. This one goes all the way from 0 to a. And so you like subtract away that unwanted area, I guess. And so you end up with the area of the trapezoid for that one specific example. But like I said before, this works for every single function that you can take an antiderivative of, not just the geometry. So it's wonderful. So big thing right here. We use the integral sign. Remember, we used it before without these bounds. We used it for antiderivatives. The indefinite integral, or the antiderivative, uses just kind of an empty sign with no numbers, and then the definite integral uses the sign with numbers. Huge, huge, huge difference. If we just do this, and we don't have numbers, and we're just finding the indefinite integral, aka the antiderivative, this ends up being an expression. So, if we took the antiderivative of x, we'd get 1/2 x squared plus c. So it's always an expression with a c involved. If I were to take this is the definite integral. It's got bounds, those bounds of integration, lower and upper. What we end up with is it's always a number. It's like the one previous example we saw, it was 21/2. And it's a number, and it represents area. Okay, so even though, these two setups look remarkably similar, there's a huge difference between them. Okay, so first example, we're going to sketch a graph of cosine from -pi/2 to +pi/2, and then use part 1 of the theorem to get the enclosed area. Okay, so nice setup here. We know cosine goes from 1 down to -1. Let's go -pi/2 to +pi/2, so just a little bit of the cosine function. Let's start with the cosine of 0. Cosine of 0, if we picture our unit circle, is 1. The cosine of pi/2 is 0. And then if we go backwards, -pi/2 is in the same spot as 3pi/2. That cosine is also 0. So we've just got like this little bump of the cosine curve right here. And then we know it would go down below the x-axis and repeat itself, but we're only interested in the part from -pi/2 to +pi/2. All right, so let's test out the fundamental theorem, see how it works. So we write this setup. If we want the area, that means we want the definite integral from -pi/2 to pi/2 of, and then you write the function right in here, and always follow it up with a dx. So this represents exactly what the question asked for. It's the area under this curve from here to here. Let's do the fundamental theorem. Fundamental theorem says take the antiderivative. So our antiderivative is, and this is the notation we use, we take the antiderivative of cosine, which is sine of x plus c, and then we do this vertical line, and we write the lower bound right here and the upper bound right here. Okay, we don't just launch into this part. There's kind of this intermediate step that we have to have first, which I guess I'll write it. So let's write f of x from a to b. Okay, so this is always the first part. I'm kind of in the wrong order here, but bear with me. So we start with this, and then we plug in the pi/2, so sine of pi/2 plus c, and then we subtract what we get when we plug in the lower bound. Oops, plus c. There we go. Okay, so the first thing I want you to notice, is that we have c, whatever it is, minus c. These guys are just going to cancel out. Okay, I'll get back to that in just a moment. Sine of pi/2, that's the top of my unit circle, that has a value of 1. Minus, and then the sign of -pi/2 is the same as the sign of 3pi/2. That's the very bottom of the unit circle. That's a -1. So this ends up being 2. Okay, so that's my answer. That's the area from here to here is a +2. Should make sense because we're all up above the x-axis. Big important note that I want to make about the C. Definite integrals. Definite integrals, that is what we're doing here when you've got the lower and upper bound. Do not need plus C. Okay, definite integrals do not need a plus C. The reason is, I mean, if we did it, they would just cancel each other out. So it's almost like a waste of our ink to even put the plus C. So the indefinite integrals, these, they need the plus C. The definite integrals, they would just cancel out anyway, and so it's not important. Okay, so let's do a handful of these using the fundamental theorem. It is a wonderful, wonderful thing. Okay, so the first thing we do is we take the antiderivative, and we just write down the antiderivative. Okay, so the antiderivative of 10x to the 9th. Remember, my power pops up from 9 to 10, and then I divide by the new power. So 10 divided by 10, and all I have is x to the 10th. And then plus, next term, my power pops up from 5 to 6, and then I divide by 6. So 3 over 6 is 1/2. So that's my antiderivative. That's the first step. This will give us a quick refresher if for some reason we don't remember our antiderivatives. Then put your vertical line and go from -2 to 2. This is just the notation that we use because I don't want you to jump right into plugging in the bounds. I want you to make sure that your work is shown out. Okay, so then equals, now in parentheses, plug in the upper bound. Okay, and then minus, now in a separate set of parentheses, plug in the lower bound. Okay, now here's a wonderful, beautiful thing that happens. 2 to the 10th, I don't know what it is. I could figure it out. I could multiply 2 by itself 10 times. However, it's the same as -2 to the 10th. I know that for sure, and I'm subtracting. So those are going to cancel each other out. This term, I could figure that out a little bit more easily. 2 to the 6 is 64. Half of that is 32, but so is this. So I have 32 minus 32, and those cancel out. So I end up with 0. Okay, so for each one of these, I'm going to give you guys a visual, just so you can see the area under the curve, okay? So I want to show you what this graph looks like. The graph of 10x to the 9th plus 3x to the 5th. Okay, so to show you this graph, looks like this. All right, just kind of a run-of-the-mill graph there. If I want the area from -2 to +2, notice you've got the exact same function below the x-axis as I do above the x-axis. Whatever area I have below, I have above. And the fact that I went from -2 to +2 brings me this perfect symmetry of a negative area canceling out with a positive area. Now, we saw something like this if you got to it in the homework a couple days ago. This is an odd function. Both the powers are odd, so it's an odd function. And we saw this, not really a theorem necessarily, but we do have this idea. If you have an odd function and you go from -a to +a, the negative area will cancel with the positive area, and you will always have a total accumulated area of 0. Not something that I want you to just jump to. I still want you to show the work, but it is kind of a cool theorem to see. Okay, next one. The antiderivative from 0 to 4 of the square root of x. Real quick, let's write that as x to the 1/2. Makes things a little easier to use the power rule. So first we write down the antiderivative. Power pops up to 3/2, and we divide by 3/2. And I evaluate this from 0 to 4. Zeros are the best thing ever to plug in, because almost always you'll get a 0, especially with polynomials. So I plug in my upper bound. Always put it in parentheses so you're doing the subtraction correctly. And then minus, then plug in your lower bound. Eventually you'll get to a point where, yes, you'll know it's just 0, so you don't even have to write it down. But for now, we're in the beginning stages, so we're going to write it down. 4 to the 3/2, that is either the square root of 4 to the 3rd or the square root of 4 cubed. Either way, you get 8. So it's 2/3 of 8, which is 16/3, and then minus, we know that is 0. Okay, so we just end up with 16/3, and that is our area. So let me show you this. Switch out the function that I just gave you, just for the square root of x. So the square root of x is entirely above the x-axis. We're going from 0 to 4, so that means the area that we accumulated was an area of 16/3. Okay, 3 more here. This one, I included this one because people get super freaked out when they see a fraction. They see what looks like a rational function, they're like, we don't know a quotient rule, I don't know how to do this, and you always, always, always forget that you can just split it up into 2 different pieces, okay? So I'm going to write that down for you. So this piece you can do 16 over t squared, which is 16t to the negative second. And then plus you can do t over t squared, which is just 1 over t, or t to the negative first. Okay, so split. Just split it up anytime you have a monomial in the denominator. And of course I am fully prepared to say this over and over again because every class I've had so far forgets how to do that every time. And it's easier than you'd think. So just split it up. And then we end up with these two separate pieces, and we can just use a power rule on these two separate pieces. Okay, so we start by taking the antiderivative. So here, let me ignore the 16 for a second. My power pops up from -2 to -1, and then I divide by -1. So I get a -16 out front. And then plus, then here, t to the negative first. That is the same as 1 over t. Okay, 1 over t, the power rule doesn't work because my power would pop up to 0 and I'd try to divide by 0. This derivative, or antiderivative, is the natural log of t. Okay. One thing that I want us to be aware of is that we're technically supposed to have absolute values around the t because you're not allowed to plug in anything negative. And so just in case, you got to put the absolute values on there. Okay. So this equals, oh, and then I go from 4 to 9. Okay, so let me plug everything in. So -16, I'm going to put it over 9 instead of 9 to the negative first. And then plus the natural log of 9 minus, then I do -16 over 4 plus the natural log of 4. Okay, so let me continue to simplify these things here. So I have -16 ninths and then minus -4. So I end up with -16 ninths plus 4. And then I have the natural log of 9 minus the natural log of 4. Okay, so two things. 4 is like 36 ninths, so I end up with 20 ninths. And then these, remember my natural log properties? If I have two separate logs and I'm subtracting them, remember I can divide the stuff inside. So it gets set up like that. All right, so weird answers there. Don't do decimals though. Leave the answers exact like this. Okay, next one. Sine, antiderivative of sine, careful with this, is negative cosine. And then I'm going to evaluate that from pi over 4 to 3 pi over 4. So in parentheses, I plug in my upper bound. Minus, and then in parentheses, I plug in my lower bound. You're going to be required to know a little bit of unit circle stuff in this section. So negative, and the cosine of 3 pi over 4. For 3 pi over 4, I'm in the second quadrant. My cosine values are negative. So we'll have a negative, so positive, root 2 over 2. And then minus a negative, and the cosine of pi over 4. We should know that is root 2 over 2. Okay, so when I add those together, I just get root 2. Because it would be like 2 root 2 over 2. And the 2's would cancel. Okay, last piece here. This is a weird one. Because we don't know what this looks like. And so I'm going to kind of set this up for you. Let me show you the graph first, so you can get an idea of exactly what we're looking at. Actually, no, we're going to come up with a graph on our own. So let's graph this parabola. We need x-intercepts. So if I set this equal to 0, we can factor it down to x minus 3, x minus 1. So I have 1, 2, 3, intercept here, intercept here. So my parabola, the original parabola, looks something like this. Right? We know how parabolas work. However, I'm taking the absolute value of the parabola, which means anything that's below the x-axis gets flipped up. So I have this little piece that's going to get flipped up above the x-axis. So my actual graph goes like this, then it bounces back up above, and then it finishes off like this. So that is my absolute value curve. So this piece right here kind of becomes like a piecewise function. Okay, so this piece from 0 to 1, just like the normal x squared minus 4x plus 3. Then from 3 to 5, it's just like this normal piece right here. So I'm trying to find this area. I'm trying to find this piece right here, this piece right here, and then from 3 to 5. So this shaded area is what I'm trying to find. So the left piece and the right piece are just like normal area under the curve. And then this is the area under the opposite curve. So I'm going to show you what we need to do. We're going to split it up into 3 pieces. From 0 to 1, it's the normal function. X squared minus 4x plus 3. Plus, then from 1 to 3, it's the opposite of the normal function because it got flipped. So negative x squared plus 4x minus 3 dx. And then plus, from 3 to 5, we're back to the normal function, x squared minus 4x plus 3 dx. Okay, so now we're going to take the antiderivatives of each piece, plug in my upper and lower bounds. So first one, antiderivative is 1/3 x cubed minus 2x squared plus 3x, and we're going to evaluate that one from 0 to 1. And then plus, let's kind of put these in parentheses here, plus, then the next one is negative 1/3 x cubed plus 2x squared minus 3x, and that one gets evaluated from 1 to 3. And then plus 1/3 x cubed minus 2x squared plus 3x, and that final piece gets evaluated from 3 to 5. All right, so we are going to plug in those values. All right, so plug in the 1, then plug in the 0, equals, so in parentheses, first I'm going to plug in the 1. So when I plug in the 1, I get 1/3 minus 2 plus 3, and then minus, when I plug in the 0, I get 0. We know that. All right, and then plus. First I plug in the 3, my upper bound. So negative 1/3 times 3 cubed is negative 9, and then plus 2 times 3 squared is 18, and then minus 3 times 3 is 9. Minus, now plug in the 1, negative 1/3 plus 2 minus 3, plus, now plug in the upper bound of 5, 1/3 times 5 cubed is 125 thirds, minus 2 times 25 is 50, and then plus 3 times 5 is 15, and finally minus, now plug in the lower bound, which is 3, 1/3 of 27 is 9, minus 2 times 9, which is 18, and then plus 3 times 3 is 9. Okay, so walk through. I need to do a lot of canceling. First of all, this whole thing cancels. I have 18 and then a negative 18. Same thing here. We don't care about the 0. Okay, so now, at this point, I mean, obviously we could do a little bit more of this in our heads. So this would be like a 1 1/3. So 1 1/3. Okay, so we've got that part covered. This, I would have, this is negative 1 1/3, but then we're adding it. So plus another 1 1/3. And then here we've got, this gives me a negative 35. And then plus 125 thirds. All right, so just to keep it going for fun here, this is 4/3, this is 4/3, that's 8/3. Combine it with this, and I get 133 thirds minus 35.
You have items to pick up in the forensics team office, room 104. Zachary Sitek, room 104, please.
And a guest appearance by Mrs. Tarr. All right, so we're going to plug this in just to get our final answer. We're super, super close to being there. All right, so we've got 133 over 3 and then minus 35. 28 thirds. 28 thirds would be the final answer. And yes, I am super well aware that you could have just plugged it in from this point. But hey, little arithmetic never hurt anyone. Okay, so these AP problems we're going to save for a totally separate day. So that's all we've got for now.